In the past few lectures, I've focused on the properties of materials, and we've seen that all of the properties of materials in one way or another result from the kinds of atoms and the way they're bonded together. Now, lecture 27 marks a transition of sorts. 2 lectures from now, I'll consider stars, which are the largest continuous objects made of atoms. First, though, we need to look at atoms in a bit more detail at the scale of the atomic nucleus. And we'll find that radioactive atoms spontaneously disintegrate, releasing energy in the form of high-energy radiation. Now, that's a remarkable statement. As scientists of the late 19th century explored the properties of more and more elements and compounds, they discovered this astonishing and completely unexpected ability of certain elements to give off nuclear radiation spontaneously. Nuclear radiation, or radioactivity, is any energetic particle or wave that's suddenly and spontaneously emitted from a nucleus. The discovery of radioactivity and the subsequent exploration of the atomic nucleus eventually led to the fields of nuclear physics and nuclear chemistry. Now, I'll begin this lecture by reviewing the nature of the atom and its nucleus, which has 2 kinds of particles called protons and neutrons. Then I'll introduce the concept of an isotope. That's an atom for which we know both the number of protons and the number of neutrons. And we'll see that all the different kinds of isotopes can be illustrated on the table of the isotopes. We'll see that isotopes can experience a number of different fates, including radioactivity, by which an atom's nucleus emits energetic radiation and changes in the process. I'll describe 3 principal types of radiation called alpha, beta, and gamma radiation, and I'll look at some of the dramatic consequences of radioactivity as well. Well, let's begin by reviewing the structure of the atom. Recall this Bohr model of the atom. It features negatively charged electrons in various stable energy states. Electrons can shift from one state to another, for example, by absorbing or emitting photons. Recall then that it was Ernest Rutherford, that's the British physicist, who demonstrated that electrons must surround a massive central positively charged nucleus. He made this discovery by firing what we called atomic bullets at the gold foil. The unexpected recoil of some of those bullets suggested to Rutherford that atoms must contain a tiny central mass. This is an essential feature of the way we model atoms today. In this lecture, we're going to explore some of the properties of this nucleus. But first, we should review the cast of players. First, we have the protons. Protons are positively charged particles with a mass that's about 1,836 times the mass of the electron. Once the nucleus was identified, it was fairly easy to characterize protons. After all, they're massive, they carry an electric charge, and it's easy to apply an electromagnetic force to a proton and observe how it accelerates. Protons are essential to understanding atoms. The number of protons in an atom, that's the atomic number. That's the atom's position in the periodic table. The name of an element is just another way to designate a specific number of protons. Single isolated protons can also be called hydrogen ions. That's an H+ ion, since the hydrogen atom has 1 proton and 1 electron. In neutral hydrogen, it's got that 1 electron, but the negative electron balances the charge of the positive proton, and it's fairly easy to strip away that electron. That leaves behind the isolated proton. And it turns out that these isolated protons are stable particles. In fact, that's an essential part of our environment. Protons occur in all water. And if there's an excess of protons over hydroxyl groups, those are those negatively charged OH- groups, then the water is said to be acidic. Recall that an acid is any water-based solution that has an excess of protons, H+ ions, in the solution. Well, as I said, it was a relatively easy task to discover the mass and other properties of electrons and protons because they're electrically charged. Scientists used electromagnets to accelerate the particles, and then they applied Newton's second law. Remember, that's force equals mass times acceleration, and you can rearrange that equation to mass equals acceleration divided by force. Scientists knew the electromagnetic force, and they observed the resultant particle acceleration, and so they calculated the mass of protons and electrons. But these measurements, they led to an enigma. It turns out that atoms typically have more than twice the mass of all their electrons plus their protons put together. And this observation led some scientists to speculate about the existence of yet another massive nuclear particle. And that would be an electrically neutral particle that has lots of mass but no electrical charge. This particle is what we now call the neutron. And it wasn't discovered until 1932. That's when the British physicist James Chadwick conducted experiments that were rather similar to those of Rutherford. Now, Chadwick's career in physics got off to a stellar start. He graduated with a PhD from Manchester in 1911, and he worked with Rutherford on radioactivity from 1911 to 1913. Well, unfortunately for Chadwick, he was visiting Germany when World War I began, and he was a civilian prisoner of the war in Germany for the entire duration, from 1914 to 1918. So after the war, Chadwick joined Rutherford as a research scientist at the Cavendish Laboratory in Cambridge, where Rutherford put a high priority in understanding the variety of subatomic particles. So in Chadwick's experiments, he fired atomic bullets at the metal beryllium, and the resulting collisions produced a new kind of particle that was as massive as a proton. But unlike protons, this new particle penetrated through several inches of solid lead. It was an electrically neutral particle, and Chadwick found that the neutron is indeed electrically neutral, which makes it exceedingly difficult to detect. The lack of an electrical charge allows the neutron to penetrate matter much more easily than electrically charged electrons or protons. And Chadwick also found that the neutron has a mass that's slightly greater than the proton. This work won him the 1935 Nobel Prize in Physics. You know, unlike protons, isolated neutrons aren't stable. They spontaneously transform into a proton plus an electron, and they release energy in the process. So the two charges, the +1 proton and the -1 electron, balance each other to maintain electric neutrality. And by the way, the average lifetime of one of these naked neutrons, as it's called, is about 11 minutes. The number of protons is fixed for any chemical element. We've seen that. Hydrogen is always 1 proton. Carbon always has 6 protons. Gold always has 79 protons. But the number of neutrons for any given element can vary widely. So for example, carbon, that's element 6. It commonly can have 6 or 7 or even 8 neutrons. And hydrogen is a really interesting special case. In normal hydrogen, there's 1 proton and no neutron. But if the atom has 1 proton and 1 neutron, it's given a special name that's called deuterium. Deuterium has a mass that's about twice that of ordinary hydrogen. That's why if you have a water molecule that has a deuterium atom in it, then it's called heavy water. And then if there's 1 proton and 2 neutrons, you call that isotope tritium. Now, lighter elements usually have similar numbers of protons and neutrons. But in heavier elements, there are typically a lot more neutrons than protons. And you can think about cramming all those positive protons into a tiny, tiny volume. The neutrons can act something like spacers in that case. Now we review this cast of character. Let's think about how we name atoms. And I want to give you exact definitions of 4 different terms. Those terms are atom, element, ion, and isotope. So, first, an atom. Atom is the most general term for all of these. Atom is just any object with a nucleus and electrons. Most atoms will have a number of protons, neutrons, and electrons combined together. So, now let's go to the periodic table of the elements. An element is an atom for which the number of protons is known. See, if we know the number of protons, we can name the element. Any atom with 6 protons, for example, is carbon. That's the entire definition of carbon. And then an ion. An ion is an element with an electric charge. So if we know the number of protons and the different number of electrons, we can name the ion. Any carbon atom with 5 electrons and, of course, 6 protons is a carbon +1 ion. If you have an oxygen atom with 8 plus protons and 10 minus electrons, that's a -2 oxygen ion. And now we come to the 4th term, that's isotopes. And the critical role of neutrons comes in here. If we know the number of protons and the number of neutrons, we can name the isotope. And there's a simple convention for this, for naming isotopes. Look at this. A carbon atom with 6 neutrons and, of course, 6 protons is the isotope carbon-12. The 12 refers to the total number of neutrons plus protons, roughly the atomic weight of the isotope. And then if you have 7 neutrons and 6 protons, you have carbon-13. And with 8 neutrons and 6 protons, you have carbon-14. The isotope number indicates the total number of nuclear particles, both protons and neutrons. An isotope name tells you just about all you need to know about an atom's nucleus. And let's look at some examples. Here, the periodic table again. The periodic table is really useful for this, so think about a few important isotopes. So we have iron 56. Iron is element 26. It has 26 protons. And it's located here in the 3rd row. that means that there are 56 minus 26, or 30 neutrons in that isotope. Similarly, uranium-238, that's located way down here. Uranium-238 has 238 minus 92, that's 146 neutrons. Protons determine the chemical behavior of an element because they're positively charged, and thus they attract electrons. Neutrons play no significant role in chemistry. They don't influence electrons, which control chemical bonding. Neutrons just make atoms heavier. But neutrons play a decisive role in nuclear physics. Now, all the known combinations of protons plus neutrons in an atomic nucleus are summarized in something called the table of the isotopes. And here it is. This table lists the number of protons on that vertical scale, and then the number of neutrons is represented on the horizontal scale. Each horizontal row of this chart represents a different chemical element. So the 6th row up has 6 protons, that's the element carbon. The 79th row up is the element gold. In other words, the vertical scale condenses the entire periodic table into one axis. And then the horizontal scale indicates the number of neutrons. For any given element, several different neutron numbers are possible. So hydrogen can have 0 or 1 or 2 neutrons. Carbon can have 6 or 7 or 8 neutrons. And iron can have almost any number of neutrons from 24 to 44. All told, there are about 2,000 known isotopes that are shown on this table. And look at this in more detail. For lighter elements, the numbers of protons and neutrons are usually quite similar. The common light isotopes thus lie close to a line that's at 45 degrees. So the most abundant isotope of carbon has 6 protons and 6 neutrons. By the same token, the most abundant isotope of magnesium, that's element 12, is magnesium-24 with 12 protons and 12 neutrons. And for calcium, element 20, the most abundant isotope is calcium-40 with 20 protons and 20 neutrons. But heavier isotopes usually have more neutrons than protons. So the commonest gold isotope is gold-197. That's 79 protons, but 118 neutrons, almost 50% more neutrons than protons. And that's typical for the heavier elements. And as I said, you can think about this situation as having positive protons repelling each other so the neutrons can act as spacers. Now, the table of the isotopes, again, this trend of increasing ratio of neutrons to protons is reflected in the chart. You see how the line curves in the direction of excess neutrons? Okay, if isotopes never changed, there wouldn't be much to say about them. But the fact is, isotopes can experience several different fates. I'm going to tell you about 4 of these fates, the fates of isotopes. In this lecture, I'm going to introduce stable isotopes and radioactive isotopes. Then in the next lecture, we'll look at 2 kinds of nuclear reactions called fission reactions and fusion reactions. Almost all the atoms around us are stable isotopes. That is, those are atoms whose nuclei will remain unchanged for billions and billions of years, much longer than the lifetime of the Earth. All the common elements have 1 or more stable isotopes: hydrogen-1, carbon-12, oxygen-16, silicon-28, iron-56. In many cases, an element will have several stable isotopes. Carbon occurs in 2 stable forms. 99% of carbon atoms are carbon-12, but about 1% are carbon-13. And nickel is an amazing example. It occurs in 5 different stable isotopes. Nickel-58 is about 68% of all the nickel. Then you have nickel-60, that's 26%, and then there are lesser amounts of nickel-61, nickel-62, and nickel-64. And let me emphasize that all 5 of these isotopes behave chemically exactly like nickel. But their masses are different because they have different numbers of neutrons. Again, the chart of the isotopes. On this chart, stable isotopes are shown in green. You see how they form an obvious curve? All the atoms around you are isotopes in this green region. That is, almost all the isotopes around you. So those are the stable isotopes. But from this chart, it's also obvious that there are a lot of other isotopes. A small fraction, perhaps 1 in every million of the atoms around us, is radioactive. These atoms can transform as a result of spontaneous changes in the nucleus. The nuclei of radioactive isotopes change spontaneously while they emit high-energy radiation. This surprising phenomenon was discovered quite by accident by the French chemist Antoine-Henri Becquerel, who lived from 1852 to 1908. Becquerel was born into the inner circles of French science. His father and grandfather were renowned physicists. He had a first-class education before becoming professor in Paris at the École Polytechnique. His major research beginning in the 1870s was on a variety of optical phenomena. Becquerel discovered radioactivity after a specimen of a uranium mineral was left in a desk drawer with an undeveloped photographic plate. When that plate was developed, it showed the fuzzy, overexposed effects of some invisible radiation. And he realized that some substance in the mineral was emitting a strange form of energy. So Becquerel began to study this unexpected phenomenon. On February 24, 1896, he reported his historic findings to the French Academy. And in subsequent research, he showed that pure uranium gave a much enhanced effect. So uranium was the very first radioactive element to be identified. For this work, Becquerel won the Nobel Prize for Physics in 1903. And in fact, he shared that prize with two other famous scientists, Pierre and Marie Curie. Once this strange phenomenon of radioactivity was discovered, an intensive effort was undertaken by chemists to isolate various radiation-producing substances. And the most successful and famous of these chemists was Marie Sklodowska-Curie, who lived from 1867 to 1934. Both her parents were teachers, and Marie was a brilliant student, but financial and social restrictions forced her to become a governess rather than to continue to a college degree. It was in 1891 she was invited to live with her sister in Paris, and it was there that her world opened up and she pursued her studies in science. It was also in Paris that she met Pierre Curie at a dinner party. That was in 1894, and they were married in the following year. So thanks to Pierre's position at the École de Physique in Chemie, Marie was able to pursue thesis research, although there was still a lot of resentment amongst the conservative male faculty about her doing this research. So you can imagine, Marie and Pierre, they agreed to work on the isolation and characterization of this newly discovered radioactive substance that was found to occur in uranium ores. And it had become apparent following Becquerel's work that uranium ores contain at least one other radioactive element that's much, much more potent. And it was an extraordinarily difficult process, requiring the concentration of more than 100 kilograms of uranium minerals to obtain just a few grams of concentrated radioactive material. Eventually, it was in 1898, they extracted small quantities of the previously unknown elements polonium and radium, and Marie's remarkable sample of 22 grams of radium chloride became an international standard for radiation levels, and it's a unit that's now called the Curie. That's the unit of radiation. All this was incredibly tedious and exacting labor. It was done in poorly maintained lab space. It was done without pay. In fact, Marie Curie never received a centime for her research at the university until 3 years after she and Pierre won the Nobel Prize in 1903. By the way, she was also awarded a Nobel Prize in chemistry in 1911. She was the only person ever to win both the physics and the chemistry prizes. But believe it or not, she was denied membership in the French Academy of Sciences by one vote in a blind ballot. And just as an aside, not only did her husband receive the Physics Nobel Prize, so did their daughter and their son-in-law. So Marie was her life was marred by tragedy, but there are many, many great accomplishments. Pierre died suddenly when he was distracted and he was run over by a truck while crossing a Paris street. And for a time, Marie completely withdrew from public life. But eventually, she assumed Pierre's professorship, and she became the very first woman ever to teach at the Sorbonne. Marie Curie is also revered because she devoted a great deal of effort to social concern. She became a leading figure in the quest to obtain more radium and apply it to human needs, especially medical applications. During World War I, she played a key role in providing portable X-ray units for field hospitals. She died in 1934 of cancer that was undoubtedly caused in part by her extensive cumulative exposure to high levels of radiation. Well, research in radioactive elements and minerals led to the discovery of 3 distinct types of radioactive decay. These types were labeled alpha, beta, and gamma in order of their discovery. So alpha decay. In alpha decay, an atom spontaneously releases a fast-moving particle called an alpha particle. And that particle is composed of 2 protons and 2 neutrons. Now, this is a strange concept. An atom is just sitting there, and suddenly, bang, a massive nuclear particle, 2 protons and 2 neutrons, goes flying off into space, and in the process, it changes the atom. See, an alpha particle is the same as a helium-4 nucleus. After all, it has 2 protons, that's helium, and it has 2 neutrons, so it's helium-4. The particle quickly picks up 2 electrons, and it becomes a helium atom in the atmosphere. Ernest Rutherford identified this radiation by sealing a small amount of radioactive material in a glass tube. He went away and let the sealed tube sit for several months. When he eventually opened the tube, he found out that it was enriched in helium gas. Rutherford had identified the alpha particle. You know, it's amazing that Rutherford won the Nobel Prize for this work several years before his discovery of the atomic nucleus. So Rutherford is one of the very few scientists to do his most important work after he won a Nobel Prize. Now, in fact, these alpha particles were what Rutherford used as his atomic bullets when he did his famous gold foil experiments. After an alpha decay, an atom has 2 fewer protons and 2 fewer neutrons. So the atom has to transform to a different element. Remember, the number of protons defines the element. Look at the periodic table. Rutherford studied the radioactive isotope radium-226. It undergoes alpha decay and gives up 2 protons and 2 neutrons, so it drops down 2 places in the periodic table to radon-222. The atomic number always decreases by 2 during alpha decay. Another common example is uranium-238. That's over here in the bottom of the table. It undergoes alpha decay to become thorium-234. Here, that is over here. Now, one reason that alpha radioactivity is important is because alpha rays are potentially dangerous. Alpha particles carry lots of kinetic energy, which converts to heat as the particles collide with their surroundings. A lot of the Earth's geothermal heat comes from this radioactivity. But alpha particles also carry enough energy that they can damage biological materials. They can kill cells. The second kind of radioactivity is beta decay. Beta decay produces high-energy electrons, or beta rays. This is a curious process. A neutron spontaneously becomes a positive proton, which remains in the nucleus, and a negative electron, which flies off at some significant fraction of the speed of light. Now, recall that isolated neutrons are radioactive and undergo beta decay. About half of them decay every 11 minutes. Each neutron becomes a hydrogen H+ ion and a speeding electron. So the study of beta radiation led to one unanticipated discovery. When this decay process was first studied, researchers found that the energy of the decay products didn't quite add up to the loss of mass. As a result, they postulated the existence of another electrically neutral particle called the neutrino, and we're going to learn more about neutrinos in Lecture 33. Well, think about how beta decay affects an isotope. Beta decay increases an atom's atomic number of protons by 1. So this process, it changes the atomic number of the decaying atom. So look at the periodic table. So, for example, carbon-14 undergoes beta decay. So it changes from an isotope with 6 protons and 8 neutrons over here to nitrogen-14. That's an isotope with 7 protons and 7 neutrons. That's over here. Okay, then there's a third kind of radioactivity. Some isotopes undergo gamma decay. These isotopes spontaneously emit high-energy radiation, electromagnetic radiation called gamma radiation. Recall that electromagnetic radiation is produced when an electron jumps from a higher atomic orbit to a lower one. In fact, any time a charged object accelerates, photons of electromagnetic radiation are produced. And the same situation applies to the positively charged protons in an atomic nucleus. Just like electrons, these charged particles can adopt different proton energy levels. Protons are usually in their ground state, but in some atoms, protons can persist for a time in an excited state. And gamma radiation occurs when one of these protons in an excited state drops to a lower energy level. In principle, it's exactly like electrons in the Bohr atom, but with millions of times more energy. Gamma radiation by itself changes neither the element nor the isotope number. The number of nuclear particles isn't altered in any way at all. So in summary, the 3 kinds of radioactivity all produce energetic rays, but they're quite different in detail. Alpha particles are big and massive, 2 protons and 2 neutrons. Beta rays are actually just high-velocity electrons, and then gamma rays are energetic photons. Now, as a consequence, these 3 kinds of radiation differ in their relative penetrating power. Alpha particles big, they crash into other materials with lots of kinetic energy, and they can't penetrate very far. Several of the early scientists who studied alpha radiation suffered slow-healing skin lesions for this reason. Surface burns and radiation. Beta rays then penetrate much deeper into tissues where they're absorbed in damaged chemical bonds. Beta radiation can kill cells under the skin. And then gamma rays are so swift and energetic that they often pass right through most solid objects. Well, now that we reviewed the three kinds of radioactive decay, that's alpha, beta, and gamma, I want to tell you about two fascinating and important characteristics of radioactivity. One's called the half-life, and the other is decay chains. So half-life is a measure of how rapidly a radioactive decay occurs. The half-life is the time it takes, on average, for half of a collection of radioactive isotopes to decay. For example, let's say you start with 1 million atoms of an isotope with a half-life of 1 day. After 1 day, you'd have only half those left. That's 500,000. After 2 days, half of those, only 250,000, and so forth. Half-lives can range from billionths of a second to billions of years. And radioactive half-lives are the basis for radiometric dating. The age of an object is determined by first estimating the number of radioactive isotopes that were contained in the object when it formed, and then you measure the amount of remaining radioactive isotopes. So the famous Shroud of Turin is a great example. The Shroud of Turin is a Christian relic that some people claim was the burial cloth of Jesus. A few years ago, some scientists tested that idea using carbon-14 dating, and here's how it works. The half-life of carbon-14 is about 5,000 years. There's a fixed amount of carbon-14 in the Earth's atmosphere, so every living thing has a small fraction of carbon-14, about 1 carbon atom in every million. Every organism has that fixed amount of carbon-14 until the day that it dies, but from that day on, the carbon-14 clock begins to tick. Every year, the fraction of carbon-14 declines in a dead body by 50% every 5,000 years or so. So if you have a small piece of cloth that was made from plant fibers, you can measure the cloth's age. By the way, it turned out that the Shroud of Turin dates from many, many centuries after the death of Christ. It's a very ancient artifact, but not 2,000 years old. Now, a second key concept is related to radioactivity. It's the decay chain, which is a connected sequence of radioactive events. Now, think about what happens when a radioactive isotope undergoes alpha or beta decay. What happens is a new isotope will be produced, and very often that isotope will also be radioactive. One isotope decays to another, and another, and another in a decay chain. So look at this. The most common radioactive isotope in our environment is uranium-238. It accounts for about 1 atom in every 2 million in most rocks and soil. So uranium-238 has a very long half-life. It's about 4.5 billion years, which is why there's still so much of this radioactive element around. Now, uranium-238 undergoes alpha decay to the radioactive isotope thorium-234, which has 2 fewer protons, 2 fewer neutrons. The half-life of thorium-234 is just 24 days. And then thorium-234 undergoes beta decay to actinium-234, has a half-life of 6.7 hours, and another beta decay takes you to uranium-234. And look at this, we're back to uranium. Then, after 3 more alpha decays, we reach radon-222, and something new happens. See, all the previous elements in this decay chain are metals. They bond easily in minerals, and so they remain in the soil. But radon is an inert gas. It has a completely filled 6th electron shell. So radon is no longer bound to the rock or the soil. It can seep out of the ground. It can concentrate in your basement. There it quickly goes through 8 more rapid decays before it ends up on lead-206. It's a stable isotope. Look at this. Bang, 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 bang. That's a lot of radiation. The concern about radon, indeed the concern about all radioactive decay, is that alpha, beta, and gamma rays are a form of ionizing radiation. Radiation can strip electrons off an atom, disrupt chemical bonds. In living organisms, intense radiation can kill cells. Radiation can also cause damage to genetic material, damage that may only appear much later in cancer and other diseases. That's why it's a good idea to get one of those radon test kits. Test the basement of your house, especially if you live in an area with high risk for radon. In this lecture, we've seen that the neutron adds great variety and interest to the world of the atom. The neutron defines the isotope, of which there are more than 2,000 listed on the table of isotopes. Many isotopes are radioactive, and they undergo spontaneous changes that emit energetic alpha or beta or gamma radiation. Even so, the energy released during radioactive decay is far less than the energy available in nuclear fission and fusion reactions, and those are the subject of the next lecture.